record. Okay, perfect. Okay, it's recording now. Perfect. Okay, and there are graphs. All right. So let's start with the definition of a polynomial. So what's a polynomial? Well, so when you think of a polynomial, guys, you should think of powers of x. So whenever you have like a combination of powers of x, then that will be a polynomial. So that's actually a definition of a polynomial. So polynomial functions are functions. So polynomial functions are functions of the form so as I said, it's just a combination of powers of x. Okay, so we have x to the power. So the power of x here could be the powers of x. They could be any. They could be any whole number. Okay, yeah, absolutely. So it's x power n. All right. So this n here, it could be any positive actually whole number. So x to the power n, and in front of x power n, there is a coefficient, and we let's denote such a coefficient by a subscript n. Okay. So a index n or a subscript n, it's the coefficient in front of x to the power n. Right. So for example, n could be, as I said, could be any positive whole number. For example, x to the x to the power 4 or x power 5, etc. Right. Then of course, as I said, you think of a polynomial as a combination of powers of x. So so let's say the highest power of x is n. Then well, before that you have x to the power n minus 1. So for example, if n is 5, so you have x to the power 5, then then after x power 5, you're supposed to have x to the power 4. So that's why we have n minus 1. So 5 minus 1, that will be 4. And in front of x to the power n minus 1, you have a number, some real number. And we denote such number by a subscript n minus 1, etc. So it's just you have powers of x, and then at the end you're gonna have x, so x power 1 here, and in front of x power 1 you have a subscript 1. So you see the power. So if you have power n, then the number in front of the x power n is a subscript n. So if you have x power 1, then in front of x power 1 you have a subscript 1. And then of course there's a constant, so I'm gonna denote the constant by a subscript 0. Anyway, so again, so we have powers of x, combination of powers of x. This highest power of x is called, this n here is called the degree. So n, this is the highest. So this n here, that's the highest power of x. Okay, and so the n is actually called, the degree of f of x of the polynomial. It's called the degree. That's the degree. Okay. So what I mean by a degree, that's the highest power of x. Then in front of x to the power n, the x to the highest power, there is this a subscript n. So this a subscript n is called the leading coefficient of f of x. So this a subscript n, that's the number in front of x to the power n. So it's called actually the leading coefficient of f of x. So again, guys, this n, the powers of x, they must be the powers of x. Okay, they must be whole number, positive whole numbers. They cannot be negative. They cannot be fractions. Okay, so the powers of x, they must be positive, or of course 0, positive whole numbers. Okay, so for example, so first example, so let's say you have f of x, negative 7 x power 6 minus x to the power 4 plus x cubed minus 2x plus 1. All right, so this f of x, it's a polynomial because, as you can see, it's just a combination of powers of x, and all the powers of x are just whole numbers, positive whole numbers, right? So what's the degree of this polynomial? Well, it's the highest power of x, which is of course 6. So my degree n, degree n is equal to 6, and my leading coefficient, that's the the coefficient in front of x to the power 6. So my leading coefficient, a subscript n, is this negative 7. Okay. Of course, guys, sometimes, the highest power of x, it doesn't have to be like the first term. So for example, let's say you have f of x, let's say you have x minus x cubed plus 7x power 5 minus x plus 2. All right, so here, what will be the degree of f of x? So be careful. So the degree, that's the highest power of x. So it's not the cube, it's the power 5 here. That will be the degree, right? That's the highest power. So the degree n here is 5. It's not 3. Okay, it's not the first power you have. The degree is the highest power, right? So it's 5, and of course the leading coefficient is the real number in front of the x to the power 5. So the leading coefficient would be the 7, or leading coefficient a subscript n is the positive 7. Okay, now, as I said, if you have a negative power, or if you have, so let's say you have f of x equals to, let's say x cubed minus x to the negative 2 plus 1, all right? So you see here, you have a negative power, right? So you have a negative power, then your f of x is not a polynomial. So this f of x is actually not, it's not a polynomial. Okay, because we have this negative power, right? Or if you have a fraction, you have a fraction as a power. So for example, let's say f of x is x power 4 minus x cubed plus x to the power, let's say 4 over 3, okay, minus 2. All right, so here we have a fraction as a power. Okay, this is the fraction here. Okay, so then of course f of x, because we have a fraction as a power, is not a polynomial. Okay, so all the powers of x, they must be positive whole numbers. Okay, not a fraction, not decimals, just positive whole numbers. Right? Is there any question, guys? Please interrupt me. Feel free to interrupt me if you have any question. Right? So yeah, so here's an exercise, very quick exercise. So we have to determine whether f of x is a polynomial or not. And if it's a polynomial, you have to find the degree and the leading coefficient. All right, so determine if f of x. So what did you say, Iraq team? Yes. Oh, okay. Well, yeah, the monomial, there's monomial, binomial. So monomial means there's one variable. Like if you have just, there's one variable like x. Binomial, that's when you have like two variables, like a plus b or x plus y. That would be a binomial because you have two variables, okay? So yeah. Determine if f of x is a polynomial. And if f of x is a polynomial, so please find the degree and the leading coefficient. All right, so 1, 2, 3, 4, 5, 6.
Professor.
Yes.
Can you go back to example 2 real quick?
Yeah, sure. Do you see it?
Yeah. All right.
So yeah, in the example 2, it's just I was saying is so I was saying that the degree, it doesn't have to be like the first power in your function f, right? Here the first power is 3, but the highest power is 5. So then your degree is 5. It's not 3, right? Yeah.
So if you have the highest power on the second term,
Yeah, it doesn't matter. Yeah, it
okay.
doesn't matter the position of your highest power, right? So by definition, degree is the highest power. It doesn't matter where is the position of your degree. Okay.
Okay, got it. Fine. Thank you.
You're welcome. Sure. So all right. So then okay. So f of x. Let's start with the first example here. Minus 4x to the 9 plus 7x power 7. Minus x6 minus 4x. All right, f of x. So here, let's say minus 3x cubed minus x to the 4th plus 2x power 6 minus 1. F of x is x squared minus 2x plus x to the power plus square root of x minus 2. F of x is, let's say, third root of x minus x power 4 minus x5 plus 2. 5. F of x is x minus 1 over x plus 1. 6. F of x is x power 4 minus x to the negative 3 minus 2. And the last one, f of x is x squared minus 1 over x plus 1 minus 2. All right. So please, guys, you have to say whether the function f is a polynomial or not, and if it's a polynomial, please find the degree and the leading coefficient. Right. So we have. I will give you a couple of minutes to think about this problem. So again, guys, if you didn't take the test last week, then I will have your final exam grade count in place of the missed test. Okay, there will be no makeup exam, right? So I will have your final grade exam grade count in place of the missed test. Let me see. So just be careful, guys, with number 5. When we have 1 over x, so let me just make a remark here. So when you have 1 over x, so you have 1 over x, right? It's, x is just 1 over x power 1, right? This is power 1 here, right? But the thing is, if you move this x power 1 to the top, it's going to be x to the power -1, right? If you move the power from the bottom to the top, then you have to take the opposite. So it's actually x to the -1, right? Yes, inverse of x, Rectim. Yeah, absolutely. So it's actually, so when you write 1 over x, it's actually x to the power -1, right? So just be careful. Yes, absolutely, Samira. Yeah, absolutely. You're right. Yeah, absolutely. 7 and 6, 6 and 7, they're not polynomials. So yeah, so for number 1, guys, we powers of x. Yes, Rectim. Yes, absolutely. Yeah, power -1. Yeah, absolutely. So for number 1, all the powers of x are just whole positive whole numbers, right? So yeah, so f of x, the first one, it's a polynomial, all right? The highest power of x is, of course, it's the degree n is 9. So this is my degree, n, and the leading coefficient is, of course, is this -4, right? That's my leading coefficient, okay? So that's my A subscript n. Number 2, well, again, all the powers of x here are just positive whole numbers. So yeah, so number 2 is also a polynomial. All right, now just be careful. So the degree here, the highest power of x, it's not 3, it's not 4, it's, of course, it's 6. So my degree n is 6. So my n is 6. All right, and my leading coefficient, the A subscript n, is this number 2 here. Okay, that's my leading coefficient, right? My A subscript n. Number 3. Well, number 3, the thing is, number 3, you have square root of x, and square root of x is x to the power half, right? And half, it's a fraction. So this power here, power is a fraction here, right? This is a power. The power here is actually a fraction because it's, it's the square root of x. So it's x to the power half, right? So number 3 is not, it's not a polynomial. Okay, now number 4, same thing. It's not a polynomial because we have this third root, and third root, that will be x to the power 1/3, right? So 1/3, of course, is a fraction. So it's not a polynomial. Number 5, it's actually, well, as I said, this 1 over x, the thing is, this 1 over x, it's actually x to the power -1. All right, so because you have power, negative power, then it's not a polynomial, right? Number 6, it's not a polynomial neither. So this is -3, right? So the power is negative here, of course, then it's not a polynomial. And the last one, same reason, you have this x plus 1 here. This is, it's a power, the power here is negative, right? So that's not a polynomial, right? So you see, guys, if you have a negative power, or a fraction as a power, then your f is not a polynomial. Okay, just be careful with that. Is there any question, guys, about this exercise? All right. So so the first 2 are polynomials. The rest is just, it's not, right? Anyway.
So the second one.
What's the problem
Why
with the second?
is -3x raised to the power 3 not a polynomial?
No. So when I say polynomial, is I'm talking about the whole thing, about the whole function. So the whole function is a polynomial. So this number 2, this -3x cubed plus x minus x to the power 4, etc. The whole thing, that's what I call a polynomial. And I said number 2 is a polynomial. So here, you see here, I said this number 2, this whole function here is a polynomial. I didn't say the -3x cubed is not a polynomial. So I said the whole function f is a polynomial, right? So when you say polynomial, I'm talking about the whole function, not just part of the function. I'm talking about the whole function, right? So the whole function number 2 is a polynomial, and that's because all the powers of x are positive whole numbers, right? Here, this is power 3, so that's good. This is power 4, that's good. And this is power 6, that's also good, right? So all the powers of x are just positive whole numbers. So that's why the whole function f is a polynomial, right? Compared to number 3, the whole function f is not a polynomial. The whole thing is not a polynomial because one of the terms here, so we have this one here, it's square root of x, so we said it's x to the power 1/2. So because this one, the power here is a fraction, then the whole function f, this whole thing here is not a polynomial. all right? So when I say polynomial, I'm talking about the whole function f, not just part of the function, right? And if one of the powers, if one of the powers is a fraction, like here, like for number 3 here, one of them here is a fraction. The power is a fraction because it's square root. That's x power half. Then the whole function f is not a polynomial. Does it answer your question? I mean, does it make sense now?
Yes.
Okay, perfect. So yeah, so we are talking about polynomials, guys, and I said, I mean, in section 2.2, we did the quadratic functions, and of course, quadratic functions are polynomials. I mean, in quadratic function, the highest power of x would be 2, right? So that's a polynomial. So let me just talk here. Let me just discuss some well-known polynomials. So well-known. Okay, so first we have quadratic functions. So we do know how to graph quadratic functions, not formula. Sorry. So we do know how to graph quadratic functions, right? So whenever the highest power of x is 2, so for example, so f of x, ax squared plus bx plus c, all right? So for example, f of x, let's say it's negative 3x squared minus 4x plus 2. That's a polynomial, right? Because you know, all the powers of x are positive whole numbers. I mean, here, when you have x, just be careful here. When you have x, oops. So when you have x, that's x power 1. Now, this is x power 1 here. Anyway, so if you check the powers, all the powers here of x are, so we have 2, we have 1, right? So then the degree, so the degree here, degree n, so the highest power of x here, that would be 2. So is it equal to 2, right? And what will be the leading coefficient? Well, it's just so leading coefficient an, it would be this number here, of course, the negative 3, right? That's the negative 3. All right. So quadratic functions are polynomials because all the powers of x are just positive whole numbers, right? 2 and 1. And the graph, we know that the graph of quadratic functions are parabolas, right? You know, oops. So their graph, so graph would be a parabola, right? So parabolas. Right. Now, next, well, if you don't have a square, let's say you have, you know, 3x plus 4, for example. So if you have just x, then that will be, so that will be what we call a linear function. Oops. So linear functions. So linear functions. So that's linear functions are functions of the form ax plus b. So for example, f of x equal to negative 3x plus 2. All right. So for linear functions, the highest power of x is, of course, so we have x, that's x power 1, right? So the highest power of x is 1. So the degree here, it's a polynomial because obviously all the powers here are just whole numbers, positive whole numbers. So the degree here, degree n is 1. All right. And what will be the leading coefficient, of course? So leading coefficient. So that will be this number here in front of x. So that will be this in the -3, right? Now, what does the graph of linear functions look like? So the graph well, if you have linear function, I mean ax plus b, then the graph should be just a line, a straight line. Okay, so the graph of linear functions is just, straight lines. Okay. Last example. So we have linear functions, and then last example. So here we have degree. For quadratic functions, we said the degree is 2. We said the degree is 2. For linear functions, we said the degree is 1. Now, can we have degree equal to 0? Yes. And that's what we call constant functions. So the third example here would be the constant functions. So what do I mean by constant functions? Well, that's functions of the form f of x equal to a. So for example, a is a number, just a random number, real number. So for example, f of x is equal to 2. So when you write f of x is equal to 2, it means that the output y is fixed, is always equal to 2. So y, the output y is fixed. Output y is always 2. Right? So how do we graph, for example, f of x equal to 2? You have here's my graph. Let's say this is 1 here, this is 2, 1, 2, 3, -1, -2, etc. Anyway, so when you say the output f of x is equal to 2, it means that, if you take any x, like for example, x is equal to 1, the output would be 2. If your x is 2, the output is 2, same. So when x is 3, we have the same output, right? It's 2. It's always 2. The output is always 2, right? So when you graph, so when you join all these points, so then the graph would be, so you see here's 2. So this is f of x is equal to 2. So for constant functions, anyway, the graph is just horizontal lines. So the graph is a horizontal lines. Okay. Now, what will be the degree of this? F of x is equal to 2. So the question is this a polynomial? Well, the thing is, you see, this is f of x is equal to 2, but you can write 2 like 2 times 1, right? But then remember, guys, we said x to the power 0 is equal to 1. Because any non-zero number power 0 is 1. So this f of x, which is 2 times 1, is actually 2 times x to the power 0. So my degree, my highest power of x, it's just the 0. Okay, so my degree n is 0, because again, this is, so it's a times x to the power 0. So my degree n is 0, and my leading coefficient, of course, that will be this number 2 here. So my leading coefficient is 2. All right. So even if you have, even constant functions are polynomials, and the degree is just 0, right? Any question, guys? Okay, there's no question. Okay, perfect. Anyway, so this is just like some, some examples of examples that we know how to graph, right? We know how to graph parabolas. We know how to graph. Excuse me? Not for me, I guess. Okay. Anyway.
Excuse me, Professor. Can you move a little bit up?
Up? Okay, sure.
Thank you.
So here?
No, I mean down.
Down.
Down. The last example.
Oh, sorry.
Yeah, I just wanted.
So next, guys, as I said, the goal is to graph polynomials in general. Okay, so the goal today, or probably next time, would be to graph polynomials, any polynomials in general. Okay, so I'm going to show you how to, well, how to graph the steps. I'm going to show you the steps to graph polynomials. All right. So first thing we're going to do, and the first piece of information that we're going to need is the behavior of the polynomials at infinity. Right. So, so first we're going to be interested in what happens in a neighborhood of infinity. So first thing we're gonna do is to study the behavior of polynomials at infinity. All right. So first, I'm gonna take some examples and show you what happens at infinity. So my first example, let's just take a parabola. Okay, so example 1, I'm gonna take just x squared. So f of x is x squared. All right, this is a polynomial. The degree is 2. So the degree is 2. Degree n is 2, which is of course even. That's an even number. All right, and my leading coefficient so this is of course 1 times x squared. So my leading coefficient a subscript n is 1, right? Anyway, so if you graph x squared, so the graph would be, it's a parabola, right? It's positive, plus x squared, so it's gonna open up. So this is positive infinity, negative infinity, positive infinity, negative infinity. Negative infinity. So this is negative infinity. Anyway, so the graph of x squared looks like the following. It's a parabola which open upward. Sorry, rec team, someone raised both of their hands. The graphs. Yes. Yeah. Absolutely. So, okay. So we said we are interested in the behavior at infinity, right? So when my x, so of course this is the horizontal axis. This is my x-axis, right? This is my x-axis, and here's my y-axis. Right? Anyway, so when x is close to infinity, or when x approaches infinity, so we are here. So here my x, my input is close to infinity, approaches infinity, right? We are close to positive infinity, right? Now, what happens to the value of the function f? Again, this is f of x equal to x squared. This is f of x equal to x squared. So what happens to the value of the function f, or to the input, the output, sorry. So the output is here, right? Which corresponds to, to positive infinity. So So what I'm saying is, if my x is close to positive infinity, then the output y is also close to positive infinity, right? And so I'm gonna just write down what I just said. So when x goes to or approaches or close to positive infinity, so this arrow here, this means x approaches. So this means approaches or close to. Okay, so when my x approaches positive infinity, or my x is close to positive infinity, then my output y, as I said, my output y is going to be right here. It's going to be also close to positive infinity, right? What about negative infinity? So if my x now is at negative infinity, right? Here's my x is close to negative infinity. The output y, the image, right, is gonna be at positive infinity. Then y approaches. Sorry. So when x is approaches negative infinity, then y approaches positive infinity. Right. So anyway, yeah, so you may ask why we are doing this. Well, it's because this is actually a general fact. So the fact is the following: if you have even degree, so if your degree is even, all right, if your degree is even and your leading coefficient is positive, here it's 1, right? It's positive. Okay, then we're gonna have the same behavior at infinity. So, this is general fact. So in general, so if f of x is a polynomial, with even degree n and positive leading coefficient, then the graph of f of x, okay, then so when you graph f of x, you know that you're at positive infinity. So here's my positive infinity, here's my negative infinity, this is my positive infinity. So when your x is at positive infinity or close to positive infinity, then your y is going to be close to positive infinity. So we're going to have this piece, this here. So at infinity, the graph is going to look like this here, okay? And at negative infinity, if your x is a negative infinity, your y is going to approach positive infinity. So you're going to have this graph here at infinity, at negative infinity, right? So we're going to use this, of course, later when we graph polynomials. So what I'm saying is, if you have a polynomial of even degree and positive leading coefficient, then you know that the graph at positive and negative infinity is going to be right here, right? Now, what about even degree with negative leading coefficient? So that would be our example number 2. So if you have f of x equals to negative x squared, of course, your degree n is even. But then your leading coefficient
Wait,
is negative.
Professor.
Yes.
Sorry, is that
Yes.
the ending of your sentence right there? In general.
Oh yeah. Then
and positive leading coefficient. Then.
Yeah. Then we have this this graph here at infinity. Right. So we have this. Yeah. Yeah, well, I mean, so again, what I mean by this, this graph is, so what I'm saying here is that if x goes to positive infinity, then y goes to positive infinity, and if x goes to negative infinity, then y goes to positive infinity. Right? So when you graph f of x, you know that you have this at infinity, you have this here and this here. Okay. Now, for negative x squared with the degree with even, so the degree is 2, which is even, of course, and the leading coefficient is -1, of course, here, which is negative. So the leading coefficient is -1, which is negative, right? So then the graph of negative x squared, so this is a graph of negative x squared. So we're gonna have, so it's positive infinity, here's negative infinity, positive, and then negative. So graph of negative x squared is gonna open downward, right? Because it's negative, you have a is -1, so it's gonna be like this here, right? So this is my negative x squared. But anyway, we are interested in the behavior at infinity. So we see here at infinity, we're gonna have, this. So when your x goes to positive, infinity, then your output y is gonna go to negative infinity, right? And when your x approaches negative infinity, so when your x approaches here negative infinity, the output y is going to be also at negative infinity. All right. So that's actually, so let me just write it down for you. So when x goes to positive infinity, then y goes to negative. And when x goes to negative, then y is going to also go to negative infinity. Right? So this is again a general fact. So whenever I graph a function with even degree and negative leading coefficient, then that will be the behavior here and here. So that will be the behavior of the graph or of the function at positive or negative infinity. All right. Now that's for even degree. Now what about odd degree? So let's have an example with odd degree. Let's take just take x cubed, f of x cubed. The degree, of course, the highest power of x is 3. That's odd. So degree of n is odd. 3 is odd. And the leading coefficient, of course, this is 1 here times x cubed. So the leading coefficient is 1. So a subscript n is 1, which is positive. It's positive. All right. So what's the graph of x cubed? So if you try to graph x cubed, then here's the graph of x cubed. So so again, we are interested in positive infinity, negative infinity, positive, and negative. So and then the graph of x cubed would be like this here. All right, so this is my x cubed. And now what happens at infinity? So when your x approaches positive infinity, right? The image output is going to approach positive infinity, right? So here's your graph at positive infinity, right? And now what about x approaching negative infinity? Well, then the output y is going to approach negative infinity, right? So here's your graph is going to be right here, down here, okay? So that's for a positive x cubed. Of course, if you take now, let's just take a negative x cubed. This is example number 3, example number 4. So let me just take f of x equal to negative x cubed. The degree n, highest power is odd, and the leading coefficient a subscript n is gonna be this -1, so it's negative, right? And the graph of negative x cubed is gonna be like, it's gonna look like, oops. So the graph of negative x cubed, so it's positive infinity, negative infinity. So graph of negative x cubed is gonna be like, right, this is negative infinity, and sorry, negative x cubed. Anyway, so what happens at positive infinity? If your x is close to positive infinity, the output is gonna be at negative infinity. Here's your output. So your graph is gonna look like this here at positive infinity, and negative infinity. Here's your x approaching negative infinity. The output y is gonna be at positive infinity. So your output is gonna be here. All right. And again, this is just a general fact. Whenever a degree is odd, your leading coefficient is negative, then your graph should look like this at positive and negative infinity. Okay, so summary, guys, just to summarize what we had here. So I'm gonna make a table. So here's my table. So here the degree n is even. Here my degree is odd. Okay. Here my leading coefficient is positive. So an is positive. And here my leading coefficient an is negative. All right. So what I'm saying is, if you graph your function f, so let's say you want to graph f of x. So f of x is a polynomial, right? F of x is a polynomial. So when you graph f of x, so in the case, if you have, if the degree is even, oh, sorry. So if the degree is even and the leading coefficient is positive, then the graph at infinity, your graph should be right here. Okay. When your degree n is even and an is negative, then the graph should be right here at infinity. All right. Degree n is odd, the leading coefficient is positive, then here's your, at infinity, this should be your graph f of x. And last case, degree n is odd, leading coefficient is negative, then here should be your the graph of f of x, right? So that's what I mean actually by the behavior at infinity, because this is supposed to be positive infinity, here's supposed to be negative infinity. And what I'm saying is, like in this case, when degree is even and leading coefficient is positive, then your graph of f of x should be right here, okay? And right here at negative infinity. Anyway, so we're gonna use this, we're gonna use this information later to graph our polynomials, okay? So this is our first piece of information to graph our polynomials. Anyway, is there any question, guys, about this table? So you see what happens? But of course, we're gonna see later the examples when we graph how to use this, right? But okay, so if there's no question about this table, so let's move to the next piece of information we're gonna use to graph our polynomials. and that would be, of course, the x-intercepts. Right. So this.
Give us a minute, please, just to copy that.
Excuse me.
Can you give us a minute to copy?
Oh, to copy. Yes, the table.
Please.
Yeah, sure. I'm gonna just leave the table right here. Okay. Now, next, so we're gonna try to find the x-intercepts, or I mean the x-intercept. We call the x-intercepts zeros or roots. Okay, of polynomials. So we're gonna need the x-intercepts and their multiplicities. Okay, so let me first just remind you the definition of x-intercepts, or the zeros or the roots. So x-intercepts, again, it's just the intersection of the graph with the x-axis, right? And how do we find the x-intercepts in general? We have to solve f of x equal to 0. So the solutions, so this is just to remind you. So just to remind you, definition of x-intercepts. So the zero, so what I call the roots, or the zeros, or the x-intercepts, so are the solutions of f of x equal to 0. All right. So the solutions of f of x equal to 0 are the roots, the zeros, or if you want, that's the x-intercepts. Again, it's just, this is, intersection of the graph with the x-axis, right? This is intersection of the graph with the x-axis. Anyway, so we know that. So we know this definition here, x-intercepts, solutions of f of x equal to 0. Now, so we need the x-intercept, or zeros or roots, and we need their multiplicities. So what's the multiplicity of x-intercept or a root? So next, so definition. So definition. So the multiplicity of the root or x-intercept, so the multiplicity of a root or x-intercept or 0 is the number of times the root is the solution of the number of times the 0 or the root or the x-intercept is a solution of f of x equal to 0, is a solution of f of x equal to 0. Right? So let me explain with an example. What do I mean by this multiplicity? Right? So examples. Okay, so let's take f of x equals to x squared minus 2x, right, plus 1. Okay, of course, this is a polynomial. This is actually quadratic function, right? Polynomial of degree 2. So we want to find the roots or the x-intercepts or the zeros. So let's say I want to find the roots. Okay, so all you have to do, of course, is to solve f of x equal to 0, right? Now, guys, first remark is that if you have, so this is a polynomial of degree 2, right? So when you solve f of x equal to 0, because the highest power is 2, then you should expect to have 2 solutions. Okay, so first important remark here, observation, so remark. Okay, so we should expect to have 2 solutions. All right, because the degree is 2. Because the degree n is equal to 2. So if the degree is 4, then you should expect 4 solutions. If the degree n is 10, then you should expect 10 solutions of f of x equal to 0. Okay, so when you solve a polynomial equal to 0, then the number of solutions is supposed to be the same as the degree. Okay, anyway, so here, this is x squared minus 2x plus 1. So we want to solve f of x equal to 0. So we're going to solve x squared minus 2x plus 1 is equal to 0, right? And we said we expect having 2 solutions, right? But anyway, I mean, this is a quadratic equation, right? So we can just use a quadratic formula, right? So if you use quadratic formula, which is, by the way, it's x equal to minus b plus or minus square root of b squared minus 4ac over 2a. Then you see, guys, because of this, it's a plus or minus here, right? That's why when you use the quadratic formula, you expect having 2 solutions, right? And that's exactly the reason why we have, the degree is 2, right? So that's why we expect having 2 solutions, because of this plus or minus, right? But anyway, so if you use the quadratic formula in this example, of course, your x would be minus b, so it's minus b is negative 2, plus or minus square root of negative 2 squared, minus 4 times a, it's 1, times c is 1 over 2a, so over 2 times 1, right? So anyway, so your x is minus negative 2, so that's positive 2, plus or minus, but then square root of what? Well, 4 minus 4 is 0, so that's square root of 0, right, over 2. So it's actually 2 over 2, it's 1, right? So actually we end up with only 1 solution, right? But we are supposed to have 2 solutions. So that means actually the 1 here, it's 2 times a solution of f of x equal to 0, because we're expecting 2 solutions, right? And then we end up with only 1, right? So this one here, it's a 2 times solution of this f of x equal to 0. But anyway, now, so how do you find this multiplicity, right? We said it's the multiplicity is the number of times the root is a solution. So what we have to do is we have to factor. Okay, so we have to factor. So let's factor f of x. Okay, so again, f of x was, x squared minus 2x plus 1 is equal to 0, right? So how do you factor this x squared minus 2x plus 1 is equal to 0? Well, I mean, there are different ways to factor, but I mean, if you know the solutions, so if you have x squared minus 2x plus 1, so when you factor, you're supposed to have, x. So it's x minus first solution times x minus the second solution. Remember, guys, we're expecting two solutions, right? Because we have x squared. We expect two solutions. So when you factor, it means you have x minus the first solution times x minus the second solution equal to 0. Right? But anyway, we know that our solution is 1, right? So this is actually x minus 1 times x minus again 1, because we have only one solution, which is 1, right? So that's equal here to 0. All right, I mean, this is x minus 1 squared equal to 0. So you see, guys, this one here, it's actually 2 times a solution of f of x equal to 0, because when you factor, you get x minus 1 squared, right? So the square here means that the 1 is 2 times solution of f of x equal to 0. So 1 is 2 times solution of f of x equal to 0. So 1 is of multiplicity 2. Is a solution, or a root, is a root of multiplicity 2. Is a root of multiplicity 2. So multiplicity 2 here. And that's because when you factor, remember, when you factor x squared minus 2x plus 1, you have, this is x minus 1 squared, right? So 1 is of multiplicity 2, because the power, when you factor, the power of x minus 1 is 2. All right? Well, anyway, this is just our first example. So let's have one more examples. So example number 2. Again, the question is, I want to find the roots and their multiplicities, right? Example 2. Let's say f of x is, let's say, x squared minus 3x plus 2. All right, and I want to find the roots and their multiplicities, right? So first step, what we have to do first is to solve. So there are 2 steps. First, you want to find the roots. You have to solve f of x, solve f of x equal to 0 to find the roots. Okay. Step 2, you want to find the multiplicities, right? Then you have to factor f of x to find the multiplicities. All right. Okay, so let's follow the steps here. First, I want to find the roots. So I have to, so step 1, I have to solve f of x equal to 0. So first, so let's here, so find the roots. So we're gonna find the roots. Step 1, find the roots. Solve f of x equal to 0. So I have to solve x squared minus 3x plus 2 equal to 0. So how many solutions do we expect here, guys? How many roots do we expect, or how many zeros, or how many x-intercept? 2, right? Because the power is 2. Absolutely, Glenn. Yeah, yeah, Monica. Yeah. Because here's power 2, so we expect 2 solutions. We expect 2 solutions. All right, so x squared minus 3x plus 2. So you know how to use the quadratic formula, of course, quadratic formula. So it's just x minus b, so minus the negative 3 plus or minus, you know, negative 3 squared minus 4 times a times c over 2a. Oops, sorry. So then, so x is positive 3 plus or minus. So it's 9 minus 8, it's 1. Square root of 1, it's 1. So it's plus 1 over 2. I saw this mistake. This is a kind of common mistake, guys. So when you have a fraction and you have like additional subtraction in the top over some number, you cannot cancel out anything here. You have to PEMDAS rule, right? So first you have to compute the top, and then you divide by 2. You cannot. So if I had 2 here, let's say, I cannot cancel out the 2. You cancel out the top and the bottom when you have multiplication. If you don't have multiplication or product in the top and in the bottom, you cannot cancel out anything, okay? So in the top here, I have plus or minus. It's not a multiplication, so you cannot cancel out 2. But anyway, of course, here I don't have 2, I have 1, but I'm just, because I saw this mistake in a couple of them in the test. So yeah, anyway, so here it's plus or minus 1 over 2. So we have, if it's plus, that would be 4 over 2. That would be 2.
Wait, excuse me.
Yes. Yes.
How did you get 3 plus minus 1?
Yeah, it's because
negative 3, when I did the math, I got 10. I didn't get 1. Square root 10.
Well, negative 3 squared, it's 9.
Uh-huh.
Right? And then minus 9 minus 8. 4 times 1 times 2, right? It's 4 times a 1 times 2, right?
Okay.
That's so it's 9 minus 8.
You know what I had
so.
did? I had did 9 minus 4, and I got 5.
Well,
I
you
did
forgot.
times 1.
Okay, but I guess they forgot the c, right? The c is 2.
No, that's what I'm saying. I did negative 3 times negative 3, 9, and then I did 9 minus 4, and I got 5.
Oh yeah.
And then I times it by 2, and I got 10. So you have to like do the multiplication first, and then subtraction.
Yeah. PEMDAS rule. Yeah, absolutely. Multiplication first, and then subtraction. Absolutely. Yeah.
Okay.
Yeah. Absolutely. Yeah, PEMDAS rule. Yeah, so we have actually square root of 1, so it's plus or minus 1. So if you have a plus, that would be 4 in the top, and if you have a minus, of course, that would be 2 over 2, and that would be 1. Anyway, so we're expecting 2 solutions, and we got 2 different solutions, right? 2 and 1, right? So my roots are or zeros or the x-intercept. So my roots are the roots are x is equal to 2 and x is equal to 1, right? Now, guys, we need to find the roots, and then we need to find the multiplicities, right? We said find the roots and their multiplicities, right? So second step, we need to factor f of x to find the multiplicities, right? So how do we factor f of x? Well, you don't have to think about it, because once you have the solutions, if you have the solutions, then you can, it's easy, it's very easy to factor. So step 2, now we have to find the multiplicities, right? Find multiplicities. Okay. So we have to factor x squared minus 3x plus 2, right? Well, how do we factor x squared minus 3x plus 2? The idea is very simple. You just take x minus, again, we expect 2 solutions, right? It's x minus the first solution then times x minus the second solution equal to 0. My first solution is 1 or 2, so it's x minus 2. That's my first solution, times x my second solution, which is 1. So it's times x minus 1 equal to 0. So you see, here's the factorization of your f of x. All right. So what will be the multiplicities of the solutions then? So you see here, it's x minus 2 to the power 1 here, right? This is power 1, and x minus 1 to the power 1. So this would be the multiplicity of two, right? And this is the multiplicity of 1. It's just the power of x minus your solution. So this is the multiplicity of 1, right? Yeah, so what I'm saying is, so the answer here would be, so x equal to 2 is a root, this is a final answer, so is a root of multiplicity 1, and x equal to 1 is a root of multiplicity 1. Again, multiplicity is just the power of your x minus your root, right? Multiplicity 1. X minus 2. Oh, sorry. Thank you, Samira. That's my mistake. I wrote 2 instead of 1. It's a multiplicity 1, of course. Sorry. Thank you. I meant 1, of course. So 2 is multiplicity 1. Yeah, of course. Yeah. So okay. Yeah. So let's have another example. So here we have quadratic equations. I mean, we know how to solve quadratic equations, but what about, let's say, a polynomial of degree 3? So let's have an example. So let's say f of x is, let's say, x cubed, all right, minus, let's see, or plus 7x squared minus 4x minus 28. Right? This is my f of x. And the question, of course, is to find the roots and their multiplicities, right? So step 1, I want to find the roots. So step 1, I want to find the roots. So I want to solve f of x equal to 0. The roots, I want to solve f of x equal to 0. Well, so first question, guys, how many roots do we expect? Right, 3, Glenn. Yeah, absolutely. So thank you. Yeah, thank you, Chang. We expect to have, because it's a cube, the highest power is 3. So we expect to have, 3 solutions. Right. Okay, so now let's try to solve. So I want to solve x cubed plus 7x squared minus 4x minus 21 minus 28 equal to 0. Of course, this is not a quadratic equation, so I cannot use a quadratic formula, right? So this is, so careful here. So it's not a quadratic equation, so we cannot use quadratic formula, right? Because obviously the power here, the degree is 3, so it's not 2, so we cannot use the quadratic formula. So how do we solve then this x cubed plus 7x squared minus 4x minus 28 equals to 0? So of course the idea would be to factor. So we need to factor, right? So we need to factor. Okay. Well, so first option is you can try to find a common factor. So question, is there a common factor? All right, here I have x cubed, this is x squared, this is x, here's 28. Well, I mean, I can say, for example, there's an x in here, x in here, x in here, but there's no x in here, right? In 28, there's no x, it's just 28, right? So actually there's no real common factor here. So no, there's no common factor here. However, yes, Amir, absolutely. However, so if you don't find like a common factor like x or something, then what we can try to do is we can try to do a partial factorization, right? You can try to do like a partial factoring here. So well, next we can try partial factoring. Okay, so what do I mean by partial factoring? Well, I have x cubed plus 7x squared minus 4x minus 28 equal to 0. So I don't have a common factor, but if you take, instead of the whole thing, and instead of taking the whole equation, I'm gonna just take, for example, the first two. If you take just the first two terms, the x cubed plus 7x squared, right? If you take just the first two terms, then is there a common factor? Yes, x is a common factor here. We do have an x in here, and we can do better than x, actually, even better than x. We can have x squared as a common factor. Yes, Elisa. So we can, so here, x squared would be a common factor. Okay, so even better than x, we can have x squared. All right, so that's the first two terms. Now, the other two terms, the minus 4x minus 28. So here, oops. So what would be a common factor here? I mean, I have minus 4x minus 28. Obviously, x is not. Yes, Leah, absolutely. So 4 or minus 4 is a common factor because 28 is divisible by 4, right? 28 is 4 times, 28 is 7 times 4, right? So 28 divisible by 4, so 4 is common factor. Mm-hmm. Okay, so let's factor out first. We can factor out. So let's factor out first x squared here. So if you factor out x squared, then to get x cubed, you're gonna need, of course, x squared times x. That will be this x cubed, and then there's a plus. This is plus here, so here's my plus, and then there's 7x squared. So here's plus 7, right? If you pull out the x squared, then you are left with 7. All right, then so that's for the first factorization. Now for next, we said -4 is a common factor, so I'm gonna factor out -4. So minus 4, and then times, of course, pull out the -4. You're gonna have x in here. There's my x, and then just be careful, guys. This is minus, and because we're gonna distribute the sign, then we're gonna need the plus here, all right? Because when you distribute the sign, minus times the plus, minus times the plus, that will be a minus. So it's plus 7 here, equals 0, all right? So once you do this partial factorization, then Well, actually it works because now I have a common factor, another common factor, which is x plus 7. Right? This is x plus 7 and x plus 7. So that will be a common factor. So I can factor out this x plus 7. So here's my x plus 7 times, right? And then if you factor out x plus 7, then you're left with x squared here. So here's my x squared. And then you are left with -4 here. So here's my -4 equal to 0. Okay, so here's multiplication, right? Again, guys, we're trying to find the solutions of f of x equal to 0. And because it's not a quadratic function, so we have to factor. Because when you factor, it means that you can write something like a product. And when you have a product of numbers equal to 0, then you know that one of the numbers is 0. So here I have this x plus 7 times this x squared minus 4 is equal to 0. Then either the first number is 0, either the x plus 7 is 0, or this x squared minus 4 is 0. X squared minus 4 is 0. Okay, so that's why the factorization is very useful when you want to solve an equation equal to 0, right? Because when you factor, you have a product, and when you have a product equal to 0, then one of the numbers is 0. So either x plus 7 is 0 or x squared minus 4 is 0. So now x plus 7 is 0. Then my x would be, of course, -7, or x squared minus 4 is 0, so you can add 4 both sides plus 4. So then x squared is 4. So you apply square root, so your x is plus or minus. Don't forget the plus or minus because you have an even power. So it's plus or minus square root of 4. So then x is plus or minus 2. So anyway, so what we are saying is that actually we got, as expected, we got 3 solutions. We got -7, and we got positive or -2. All right, so we have, as expected, we have 3 roots. So 3 solutions. So x equal to -7, x equal to +2, and x equal to -2. All right. Now, so that's the roots, right? 3 solutions or roots, if you prefer. Okay, so that answers the first part of the question, the roots of the f of x equal to 0. Now we have to find the multiplicities, right? I have to find the multiplicities of -7, +2, and -2, right? So second step, step 2, the multiplicities. So step 2. Oh wow, I have only 2 minutes left. Wow, the time really goes really fast. Anyway, so it's fine. I mean, we're gonna continue next time, but let me just explain the multiplicities here. So as I said, we have to factor. So we're gonna find the multiplicities. So we have to factor, you have to factor this x cubed plus 7x squared minus 4x minus 28 equal to 0. So guys, we said we were expecting 3 solutions, and we got 3 solutions. So when you factor, you're supposed to have something of the form x minus a first solution times x minus the second solution times x minus the third solution, right? Because again, we are supposed to have 3 solutions. So that's why we have x minus first solution, x times x minus second, x minus third solution. So So my first solution is, so that's x minus, first solution is -7. So I have x minus -7 times x minus the second solution. It's 2, right? My second solution times x minus -2. That's my third solution, equal to 0. So what I'm saying is that this is the factorization, though. This is the factorization of, of f of x, right? Now, of course, here, this is just power 1 here, this is power 1 here, and here's power 1, right? So then,
I have a question though.
yes.
For the in the middle one, it's supposed to be +2, right? Not -2.
So here, no, it's x minus, the second solution, which is 2. So it's x minus 2. But then you see,
Okay. Oh,
because
got it.
here, the third x minus -2, that would be the x plus 2 you're looking for, right?
Okay, got it.
So now, so the first solution, which is -7, right? The -7 here, here's my second solution, and here's my third solution. So -7, the multiplicity of -7 is just 1, because this is power 1. So multiplicity of x equal to -7 is, well, it's just power 1. So here it's 1. Same here, multiplicity for +2. Is 1, right? We got 1 here. And finally, multiplicity of -2 of -2 is also 1. All of them have the same multiplicity, which is 1, right? Anyway, I will see more examples, I guess, next time. And you may ask why we are doing this multiplicity thing. Well, because I'm going to explain it next time. But the multiplicity of the root is going to give us like another piece of information we're going to use to graph our polynomials. Okay, so this multiplicity thing is really useful. It's going to be useful to graph our polynomials. So I'm sorry, guys. I went over time. We're going to do more examples next time, and we're going to continue the same section, I guess, on Wednesday. Okay, so I'm going to stop here, guys. Please let me know if you have any question or any suggestion, all right? Thank you, everyone. I'll see you next time. Take care and stay safe, of course.
Professor,
Thank you.
Professor.
Yes.
Another question. So why do you say that the multiplicity of x is equal to 1? Why is the 1 there? Like, I don't understand the 1.
No, here it's 1 because it's just because, I mean, because there is no power here, so it means that's it's a power 1. If you yeah, because there's no power there, then it's just power 1. But you know, like in the previous example, we had where is it? Like here, you see this x minus 1 times x minus 1. So we got x minus 1 squared. So we said that's the multiplicity is 2 because the power is 2 there, right? Yeah. So I mean, if you don't have any power, it means it's power 1. So that's why multiplicity is 1.
I got it. Thank you.
Thank you. Thank you, everyone. I appreciate. I will see you next time. Take care and stay safe.
Wait, Professor.
Yes. Yeah.
Is there a homework going on today?
No.
Or is it gonna be on Wednesday? All right.
Yeah. No, there will be no homework actually this week. I'm gonna take a break. I guess until next week. Yeah, I will probably assign homework next week.
Thank you.
Thank you, guys. See you next time.